I can do that then. Okay, so that means I should start now. And now we go ahead and stream. Okay, so that should be doing it. I think everybody can hear me. Good morning. Thanks everybody for joining. And hopefully you have good air to breathe. If you have an AC, it usually helps. If you have a heater, it usually does not help. If you have any filter, turn it on. That definitely does help. If you're still on the other end of the continent, then congratulations, that choice helped right now. Because the air can be, in California, the air is really bad. In Berkeley, it's basically unbreathable. Let me know if this, by the way, causes anything, because there's a bunch of, it can really cause claustrophobia, and it can cause a bunch of things. And if you feel you have problems or you just don't feel right mentally or something, this is nothing to be ashamed of. This just happens. You know, you can reach out to me and I can forward you, but Physico has a bunch of resources. But I'm just saying, I'm here for whatever happens. I mean, obviously, I can connect you to professional help. And it's really knowledge of mental health has with COVID went up factor 3 mental health issues. So now we have COVID and the wildfire. And one thing I can tell you, don't turn on the news. Okay. So for now, I think the best thing to do is to not panic, you know, and do things that calm us down, including, in my case, it's doing a bunch of science. I really enjoy doing science. That's why I'm doing what I'm doing. So today, and everybody can hear me right, I hope. Today we're going to talk about memory cueing capacity of Perceptron, and we're also going to talk about the memory cueing capacity of a whole neural network later. And it's very important. These two lectures are like the hardest two lectures, okay? If you get through these two lectures, after that you start to be ready for your project, and I will talk about your project soon. There's also going to be a homework 1. It's online now. I wanted to put it online last week, but hey, I got delayed due to Labor Day, so they're going to office hours. And since the homework is voluntary anyway, and it's more like something we discuss in office hours, I decided to just delay it by a week. So you have, basically the homework is online now if you go onto the class website. And if you do it now, it's sort of, we want to have it discussed next Friday. So if you want to take a look at it over the weekend, then we can discuss it in office hours and maybe discuss a little more among yourselves during the week or on Piazza. And then on Friday, we'll discuss it in detail. These are just, this first homework is mostly understanding and working with information a little more, because despite the fact that most of you are computer scientists, and also despite the fact that I'm a computer scientist, I learned that working with information is for some reason not something that we learn very much and have very intuitively. In fact, all the programming, especially Python, tries to have us get rid of that notion, while it's actually the essential notion for computer science is information. I'm trying to correct this a little bit by giving you some practice, and so that's what the homework is for. Don't worry about the project right now, but if you want to, for example, use the homework on Piazza or in general as an opportunity to connect with other students, you're totally welcome, because I will at some point ask you to form teams, and so you can start working on your projects. And I know this is very difficult. This is much easier when the lecture is actually physical. In fact, this is so much easier that this lecture was approved for being physical, but given the air quality and COVID, we are far away from making it physical. So again, I think the office hours are something where I can help you in this regard. And of course, the best thing would be if a bunch of people come to the office hours, then you can just informally talk about it. So in general, office hours is nothing where I give you something. Office hours is something where you pull, right? Where you ask, I have this question, what do I do here? What can I do? And I'll just be here and try my best, okay? And definitely keep stuff on Piazza. I know Piazza is an undergraduate tool, but I don't see any reason that works really well to use it in a graduate class. I know this may be a little different for you than what you used, but hey, you know, let's use what works. That's what I'm thinking. So let's do that for now. So the office hours will be Monday, every Monday, 1 to 2 p.m. This Zoom link, okay? The reason why I don't publish this Zoom link everywhere, like on the website or also on the slides, which will be on the website, is that I don't want trolls to come in and stuff. I want this to keep this class, the integrity of this class, so you can, you know, you can all work together as a team on, you know, working on experimental design. So, any questions about this? I'm gonna open the chat just for me to have it there. Okay. So then, let's talk about the refresh with the memory arithmetic. Okay, so these are now the first couple of slides again that we already discussed. And please, if you have questions, right now is a very good time. So Shannon created the notion of saying information is reduction of uncertainty. And that's very, very interesting because we all have a middle school notion of what uncertainty is. Our middle school notion of uncertainty is probability, right? So basically, the interesting part though is that probability itself is just a number that quantifies the uncertainty. But the reduction of it can also be quantified, and that's information. And the funny thing is the reduction of probability, basically of like making it less and less and less and less and less and less unlikely that I don't understand what's going on, is for some reason logarithmic, which is interesting. So in the end, we have this notion which is log2 of a probability minus log2 of a probability is the Hartley entropy, or basically the entropy in the case of the uniform distribution. And that at this time, which is interesting, is the same as the log2 of the number of states, which is what we learn in computer science as how you convert numbers from decimal to binary. So that's basically called, and then Shannon also introduced something called bits. Now, converting numbers from decimal to binary and how many digits we need for that, the log2 of that seems not so surprising. What's more surprising is that we can measure uncertainty in bits, because that means any kind of uncertainty you have is finite, right? So you can obviously zoom infinitely, but once you have a zoom level, it's a finite number of states. And the reason for this is that the bit is kind of undividable, right? You cannot get less than a bit, right? The one atom is sort of what Socrates created and said, let's understand nature by thinking of atoms. And of course, then physicists go and say, yeah, but there's a nucleus and then there's electrons. So they zoom in further, further, further until they're right now at the Higgs boson. But in the end, when you have a concrete problem that is at a certain zoom level, you know, you can work with that, and you have maybe a really, 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 really large amount of uncertainty, but it's never infinite. It's not uncountable, and definitely it could be huge, but it's also just countable because it's a number of bits. It's just like number of atoms. It's never infinite. Even the universe is finite. So the trick here is that with that trick, we can do a lot of things. And with that trick, we basically have the atom of information being the finite state transition. Now the finite state transition is what you have as an arrow in the finite state machine that we draw. It's what you have an arrow in the transistor symbol that you draw. Or if you want to think about this as much easier, it's just a switch, right? It's just when you switch the switch, that is the finite state transition. And you finding out whether the switch is on or off is one bit of uncertainty at the maximum. There cannot be about a single switch. There is no more uncertainty than one bit. There could be less because sort of on average, you could know about more switches, but for a single switch, knowing anything, you can either know the state, it's on or off, then there's no uncertainty, or if you don't know the state, it's one bit of uncertainty, which is, can be on or off, but I don't know it. And that's very, very essential to the way we will deal with machine learning and uncertainty, because basically we will end up counting bits. Yeah, and then Shannon said, well, statistically speaking, if you have a lot of switches and there's some dependencies between those switches, then there's the Shannon entropy. And that provides us a tighter bound of how many switches could actually use this. And so I'm stumbling a little bit because here's what's really interesting. When switches are independent, okay, so that means it doesn't matter that these switches, that one switch is down for the second switch, right, or for the third switch. When switches are completely independent and each of them can be operated independently, that's when each switch has one bit. But here's what's interesting. If you had switches that were dependent on each other, then the first switch, for example, if they were in series, then the first switch would make a difference whether the entire circuit, whether the light is on or the entire circuit actually lets the electrons through. And so now we have the situation with AND and XOR and NAND and these kind of things. And we'll talk about this a lot in this lecture. But that's the situation when you have dependencies where it does matter that these are not independent. And now here's the big interesting question. What do we know from probability theory? Everybody remember the base rule that corresponds to what I just said? Right? So the base rule, I'm just, Randy, remember the base rules?
Sorry, I don't quite remember.
You don't remember? Okay. Alan, anybody remembers the base rules?
Is it that probability sums to 1 and it's not negative?
Okay, so probability sums to 1 and is not negative is not the base rules. That's how you define a probability space, but it's a very important notion that we need to keep in mind.
Is it probability of A given B is equal to probability of A and B over probability of B? So like A and B are two different events.
Exactly. So that is basically, these are the base rules. And one of the most important base rule is that if two probabilities are independent, okay, so if probability of A is independent of the probability of B, then the joint probability is P of A times P of B, if they're multiplied together, okay? And now the bigger trick is that base doesn't tell you anything about what if they are dependent. So I'm bringing this up because there's a huge field of Bayesianism in machine learning, okay? And they're obviously doing the right thing. They start from first principles with Bayes rules, but there is one problem. The problem is that the case where all probabilities are independent is actually the least interesting case, because all we can do about this case is we can guess. If we guess A right, it does nothing for us for B, because B is independent. So that means that we basically can really, really easily find out how difficult it is to guess using Bayes. And it's better than a random guess. But the trick is when probabilities are dependent, then we have to ask ourselves, what is the model of dependency? And that's cool. We can also use that using Bayes, but we have to be careful. It's not the principal Bayes rules. So what we do then is we start to say, let's model this. Let's figure out how dependent things actually are and in what case. And then you create the notion of a probability distribution, right? So, and that's how statistics gets to the point of saying, okay, maybe it's a Gaussian, maybe it's different distribution, okay? So I'm just giving you this because I wanted to have a statistical idea in mind too. They're not wrong, right? It's just then it becomes interesting. So now, again, the thought framework, machine learning. We did this before. We said we have a table that we convert into combinational logic, right? And then it's basically how many state transitions n need to model the training data. And that is our experimental design problem. Our experimental design problem is to find out how many states would we actually need. And now states, again, in the equiprobable case, is 1 divided by the number of states. And if there's dependencies that we can exploit in a smart way, then we need to draw less arrows, we need to use less switches, we can use less transistors, then we can exploit the dependency and actually do something with less state transitions than if I had to model each variable independently. Now, we had the idea of intellectual capacity, which is the number of target function a machine learner is able to represent. And then most importantly, we have what we call the memory equivalent capacity. So the memory equivalent capacity is a machine learner's intellectual capacity. A machine learner's intellectual capacity is memory equivalent to n bits when the machine learner is able to represent all 2 to the power of n binary labeling functions of n inputs. And what this means is that you have data and then an arrow to an outcome, data and then an arrow to an outcome. And that's basically your lookup table. So your lookup table can obviously store all binary functions, right? Because the lookup table would be nothing else but what the logicians call a truth table, okay? And the math we do today will have to do a lot with truth tables and how to get to that notion. So what I said last time is basically what the next 2 lectures will be about. Supervised machine learners have a memory capacity in bits, and that's computable and measurable, okay? This depends on your machine learner. And artificial neural networks with gating functions have a capacity upper limit that can be determined analytically using 4 principles, an effective capacity that can measure it in actual implementations. Predicting and measuring will be what the interesting thing is in the whole class. So let's go back to the very basics and think about neurons. Why do we think about neurons? Because right now I think on everybody's mind is deep learning, right? Each of us seems to be swept with a wave of deep learning. Deep learning seems to be able to solve everything. Now, some people say, nope, I'm holding on to my random forest, or nope, I'm holding on to mine. It's fine. Everything I explain here will work with that as well. But we will use as an example the perceptron. Now, who invented the perceptron? Well, the word perceptron was invented by Rosenblatt. I think everybody should know this. It is really worth it to read the original publication from Rosenblatt, okay? The original publication from Rosenblatt is a lot about information, really interesting. That notion got lost in the long journey over to deep learning. Then, however, Rosenblatt is not the only inventor. It was also invented by a person called Bernard Vedral. He is a Stanford emeritus, and he in 1956 created what he called the Adeline, which was a specialized filter. What he wanted is a switch that doesn't switch based on signal, right? So for example, if you have a relay and there's a signal, it switches you, so you can do that. Or if you have a transistor and you put a voltage to the base, it switches, right? No, what he wanted is a switch that instead of switching on a signal, it switches based on an energy, and that is a signal over time. So what that means is that you have to charge something first and then it switches. And now that's funny, and that's interesting, because that actually is a neuron, okay? So why do we have neurons in our body? It helps us to pay attention. So, for example, our skin is full of neurons. But are you thinking about your about your pinky toe right now? No, you're not thinking about your pinky toe right now. I mean, right now you are, because I'm talking about your pinky toe. You're talking about your pinky toe if it is in pain, right? You're talking about your pinky toe if I step on it, or you think about your pinky toe if it became cold, or all of these kind of reasons. Well, your brain wants to focus on survival, and if your pinky toe is fine, we need to focus on the pinky toe. There's no need. We need to focus on maybe the gorilla in front of us and run. And that's the idea. So the idea is that if the energy threshold is high enough, we want to ignore signals until there's so many signals that the energy threshold is reached, so that the neuron fires and sends, an impulse to the brain, which, by the way, also contains a lot of neurons. So in the end, it has to do with basically relevance compression. Okay, so we compress, or we basically ignore what's irrelevant to focus only on what's relevant. So people are really good with ignoring things, because that's what we are hardwired to do. That's what a neuron is supposed to do. It's supposed to ignore the stuff that doesn't matter. And so now, how does it work? Well, it works as depicted here. You have a bunch of inputs, and these are just the typical inputs we have in our table, right? So x1 to xn are our columns of the table. And then we program the neuron, right? So we basically need to learn weights for these inputs, which we call W1 to Wn. And then we sum up the dot product of the Wi times xi. So that's just nothing else but multiplying a Wi with an xi and summing them up. It's really, really simple. And as you do so, you get a number. And now the bigger question is that number larger than the threshold or smaller than the threshold? And if it's larger or equal than the threshold, fire. If it's not large, if it's smaller than the threshold, don't fire. And that gives you a binary decision function. And the binary decision function, by default, looks like a step function. You see it here. It's just a half rectangle, right? It's totally clear. So now by default, the output is 0, 1. Okay, I know you probably work with ReLUs and with sigmoids and these kind of things. There's a little different. We'll talk about that just in the next slide. For us, we will use the rectangle function as a mental model, and I will show you why. Now, before I go there, one important question is, why are we using the dot product? And the interesting part about the dot product is that the physical interpretation is that it's an energy. So, for example, if you have solar panels on your roof and different angles, you would use the dot product to figure out how much energy in total can these solar panels produce, right? It would be each solar panel as sort of the weight of efficiency, and then the efficiency depends on the angle, and then each incoming sort of sun as the x, right? So for physical interpretation, and I gave this to you before, it's an energy threshold, but it's interesting because you probably have heard a bunch of other interpretations of why we use the dot product. And one of them probably is to decorrelate, right? It's not wrong. It's what energy does. But the actual root physical interpretation as of the inventors of that thing we call Perceptron or neuron now is an energy threshold, because biology is the root cause interpretation of that. Any questions about that? Okay, so then I'll move on. And if you now go on Wikipedia, you see all these activation functions. The binary step function is the second row here, is what I just showed you. But then there's the logistic function, tangents hyperbolicus, arctangents, soft sine, ReLUs, super hype in deep learning right now, and then leaky, leakified, rectified unit, and so on and so forth. For our interpretation, the first one, identity, would make a difference. All the other ones will not make a difference. They are just workarounds around the fact that we use statistical gradient descent to actually train those networks. And there are certain advantages of a rectified linear unit when you do that. For example, the fact that you get the whole bit of information here. The whole information is passed on, not just a bit. But then again, not really, because let's look at the next one. When we have an information and a probability view, the main question we ask is what is the probability that the decision is 0 versus what is the probability that the decision is 1? And if the shape on the left, like under the curve, is the same area as above the curve, well, on what does it really depend then, what the probability is? Any guesses? Again, I do guesses. Guesses is fine. Okay, so you can be wrong. It's totally fine. This is a very new notion of doing things, and requires intuition that we're all going to work on. So, okay, I'm just going to call somebody out. Aditya, any intuition? Okay, Aditya is maybe not listening. Randy, calling you again. I don't know.
Mm-hmm.
I'm on you right now. Sorry, because you're in my Zoom. So Randy, so when the question was when the errors under the curves are the same between like below the curve and above the curve, what's the default assumption for what the probability is that we are under or above the curve?
Yeah, sorry, I'm not sure either.
It's 50%.
Mm-hmm.
Doesn't matter where we are, right? Because if we don't know where our points fall, right? If you throw random darts at this curve in front of you right now, you'll have a 50% chance of hitting above and 50% chance of hitting below the curve, right?
Mm-hmm.
And what this means is that what would happen if I now change the shape of this threshold function? What if I make it a reload? What if I make it a step function? As long as the area above and below the curve is the same, it completely depends on the data whether I get 50% chance or it's 40, 60 or 30, 70. Does that make sense?
Yeah.
That's great. So Arjun, does that make sense?
Yeah, so it's essentially like if you condition it, then it's going to be out of bag. It's not going to be equally likely. But if you just throw darts at random, it's going to be random. Is that it? Like 50%?
Yeah, so if you don't know anything about the data, you have to consider this throwing darts at random, right? You have to consider this, that you throw the darts but then maybe you have a bias now because you use your left hand or something. And that bias makes you hit more above the curve rather than more below the curve. Well, then the probability would be not anymore 50-50, right? Then it would be 70-30.
Makes sense.
And now the log 2 of that would make it less than a bit. And the log 2 of 50-50 would make it 1 bit. And so now this is a very, I spend a lot of time on this slide, and this is because while you see on Wikipedia all of these different functions, it doesn't really matter what the activation function is. What matters is, when you have a threshold, when you ask smaller equal or smaller or greater, when you have a threshold, The question is, how often are you hitting above and how often are you hitting below this threshold? And the maximum amount of information you could gain, not knowing if you're hitting below or above and then doing the experiment, is 1 bit. Why? Because if your input is completely random, if it's a coin toss and you say, I'm hitting above the curve when it's head, and I'm hitting below the curve when it's tail, that is 1 bit of information or a 50-50 chance, right? And now if the coin is biased, well, yeah. Now, so the most important thing about activation functions is that they are symmetric, that they don't introduce their own bias. And now we can go back to activation functions again and actually see that this seems to be mostly true for all these activation functions. Again, the only function that is different here is the identity, because that's not a threshold, that's just passing through, okay? But after the identity, you see all these functions are symmetric, and that means that there's a 50-50 chance, given uniform random data, that we would fall above or below the function. And that means it's not dependent on the function. It is dependent on the data. So knowing that, we can start to ask ourselves, what are the structures of the data in general, sort of like, what do we know about data? When does it fall above and below a threshold, right? And that's an interesting task. And that task was actually introduced by Marvin Minsky in 1967. And Marvin Minsky in 1967 went ahead and said, well, we can draw a line in a coordinate system, right? So we can go ahead and have the perceptron draw a line. I mean, to be frank, Rosenblatt already did a lot of this, but he became more systematic. And he said, okay, the line is obviously linear algebra, right? Because we have the line defined as something like this, that 0.9x1 plus 2x2, and then a threshold greater equals 1, right? So this is the line that we're representing here. And now the question is, as we have this threshold, are things below or above this threshold, right? But it's interesting because obviously we have now two kind of things that are unknown, because we don't know what the weights are. Because for some concrete weights, you can tell me is this below or above, because all you need to do is do that math. The other problem is, what is the data, right? So given the data, you can say, okay, I can separate this by wiggling out the weights and figuring them out. And we do statistic gradient descent for that. Or given the model, you can go and say, give me your data, I'll tell you what the model does. But the question I'm asking now is really intricate. I'm asking, not knowing the data, not knowing the model, what can that thing called perceptron actually do? So what Minsky did, he said, okay, maybe we normalize the data somehow. Maybe we go and make the data Boolean functions, okay? And this is now the Boolean functions. So the Boolean function of two variables, for example, are obviously, that's pure computer science, right? So you have two Boolean variables, x1 and x2, and your input comes 0, 0, 0, 1, 1, 0, 1, 1, okay? Who has not done this in 61C to the point where they started saying, I don't want to ever see this again, okay? I'm sorry, you have to see this again. So basically what happens here is you have these two Boolean variables, right? These two switches. They can have these 4 states. In general, 2 switches can have 2 to the power of 2 states, or n Boolean variables, or n memory cells, or n switches can have 2 to the power of n different states. And now these 2 to the power of n different states can now be mapped onto 2 to the power of 2 to the power of n different labeling functions. So if we restrict ourselves to completely binary input and completely binary output, then we can actually, at least for 2 variables, find out and draw out all the 16 different target functions, because 2 to the power of 2 to the power of 2 is 16. All the 60 different labelings that we could make out of these variables, okay? And now, Marvin Minsky went ahead and said, okay, now I want to know a single perceptron. Can we actually train all these 16 Boolean functions? And Marvin Minsky was angry, furious. He said perceptrons are garbage. Why? Because with a single perceptron of 3 parameters, where it's like 2 inputs, 2 weights, and the threshold, that's 3 parameters, you can only label 14 of the 16 functions. You cannot model all of them. And he tried to figure out why on earth is that. Every geometry just basically told him, yeah, it turns out it has to do with linear separability. The point is that if you look at your cube down here, or it's a 2D cube, right? So at your rectangle with the or and end, it is obviously very simple to put an or an end to separate those with a single line. But you will find out there's just no separation between sort of that you can make so that you get 100% accuracy for XOR and not XOR. And there's something very profound about not XOR. Does anybody know? So I think everybody knows XOR, but have you ever thought about the fact what not XOR actually is? And I'm again taking random people. So Ravina, any clue what not XOR is? You're not sure. So let's take a look. Does anybody know which one is not XOR in this graph, F1, F2, F3? Which one is not XOR? F9, totally right, Eleanor. Yes. So if you look at F9, Ravina, what does it tell you? When is it true? It's true when both x1 and x2 are false. No, F9 is true when both x1 and x2 are the same. Okay? So when x1 and x2 are the same, then F9 says true. When x1 and x2 are not the same, then F9 says 0. So you're totally right. It's true when both x1 and x1 are false, or when both x1 and 2 are true. Completely right. So how do we call this in general? We call this equality, okay? So not XOR is the equality function of 2 Boolean variables. And it's very profound because equality cannot be implemented for 2 Boolean variables with a perceptron. And that is much more interesting than XOR for me. You know, XOR is the famous example. And we will learn that the reason for this is that equality is not compressible. You cannot compress equality. In order to check whether 2 things are equal, you have to read each element and you cannot skip any decisions. So you need to make a decision for each single element in order to find out if something is equal. That means there's no generalization there. You cannot compress. Right now, just believe it. I will explain that in detail. But the interesting part here is that I already started to make a compression argument, and it turns out that this is how you solve Minsky's problem for real. Now, before we go there, I want to give you a little more intuition of some orthogonal concept And that's very important because you have heard that a million times if you've done anything in machine learning. The orthogonal concept is the Vapnik-Chervonenkis dimension. VC dimension. VC dimension is defined just as said here. The VC dimension of a hypothesis space F is the maximum integer D. D equals dVC, such that some data set of cardinality V can be shadowed by F. Shadowed by F means that any arbitrary labeling can be represented by any hypothesis in F if there's no maximum host VC level. Let's be a little more precise. What is this saying? What is this saying is you have some set, right? And obviously, all possible binary labelings of this set would be 2 to the power of n, where n is the number of elements in the set. This is the same as saying the power set has 2 to the power of n elements in when the set has n elements. You must have seen this before. And now shattering means if you can basically label, if you have a set with n dimensions and you can label all of power sets, if you're able to basically model all the power sets, possible power set, with that classifier, then that is your VC dimension. So the VC dimension would be the largest number of elements where this is true, okay? So the VC dimension is 10, then 10 would mean you can absolutely model all 10, you can, whatever labeling of the 10 elements you come up with, you would be able to model that with a perceptron. So for example, for a machine learner, for the perceptron, here the VC dimension is not 4, right? Because what we had here was 4 different rows in our table. And we found out that we cannot label all different 16 labelings. We can only label 14. So for the Minsky problem, the VC dimension is 3, okay? I can just tell you that if you will try this out, for all of these 16 functions, you can always get 3 correct. So the VC dimension for Boolean variables for a single perceptron is 3. And that's a problem because there are 4 states, so it doesn't work, okay? So that is one way to solve the Minsky problem, but there's a big freaking problem with this approach. Now, I really don't read secondary literature on VC dimension. Please read the original literature. Go to the original paper from Vapnik and Chervonenkis. It's a huge paper. But if you go to VC dimension, he explains this actually pretty well. And his second example is something really interesting. It's the sinus. He's saying the VC dimension of the sinus wave is infinite. Well, why? Well, because if your points are just in the right position and you label them 0, 1 if they are basically 0 if they're below the sinus and 1 if they're above the sinus, you can find with one parameter, right? You can totally label infinite points. And that's awesome. But the problem is here the notion of sum set, right? So for the sinus as a separator, there exists point set that could be infinitely large in the attributes such that you can label all of them. And that's great. But that's not the situation we have when we do machine learning. Because the situation we have when we do machine learning is that we don't know the data, right? If I already knew the constraint that a sinus wave would separate them, oh, congratulations, just use that sinus wave, right? But what we have is some random machine learning task, and we don't know. We just have some gigabytes of data and 100 million videos. We don't know, right? It's very, very unlikely that a sinus just does this, right? So what we need in order to find out what the upper and lower limits are is not some set, not the solution for Minsky's problem or some other problem we come up with this. What we need is, given maximally bad data, the worst case data, what would be the best thing that machine learner can do? And that was investigated by Thomas Cover for the Perceptron in a very seminal paper in 1965. And then what I do like to give you is chapter 40 of David McKay. David McKay went and said, here's how we solve this problem with the worst case scenario. What we do is we basically interpret the machine learner as an encoder and decoder in a Shannon communication channel. Now, many of you may have heard about it but never worked with it. The good news is, for this type of understanding, you don't actually need to work a lot with the Shannon communication channel. It actually is totally okay to just think about the channel like it is on the slide. So the channel originally from Shannon is we have a sender, and then the sender wants to convey a message. And now the encoder goes and says, okay, whatever message that I don't know yet, I will encode into a signal that will transport over noise, which is interesting. So the channel, it will transport over a channel that has noise. So it's like telephony, right? So you want to be able to say what you want to say, and then it's encoded into something that goes over a telephone line. And the telephone line may have routing delays, it may drop packets, it may have analog noise dropping in, it may have all kinds of issues. But what we want is that after that, there's some kind of thing, after sort of, things were changed quite drastically, arrives at the receiver cell phone. And that's good enough so that a decoder can reproduce your original what you said. Okay, so that's the original communication problem from Shannon. And it's kind of not a surprise that he worked for AT&T Bell Labs when he came up, right? Because AT&T. So now, how do we apply this to machine learning? Well, let's get rid of the channel. We say the channel is just hard to trace, 100% correct. Let's do this. We say, what we really have is we have some data, like our two Boolean variables from Minsky, right? X1 and X2. So we have some data. The data is, however, available to both the encoder and the decoder, okay? So we will say, whatever data it is, let it be available, okay? And then would you go and say, however, I want to know, can a perceptron serve as an encoder of the labels, given the data, into weights, like parameters of the perceptron, into weights and thresholds, such that when somebody only has the weights and the thresholds and the data, it can be reproduced by 100%. So that is the equivalent of saying, let's test on train. Okay, so let's take some training data, train it, and then let's test whether the perceptron memorized the data with 100% accuracy. Okay, and the main trick here is to say, well, for perceptron, let's just use uniform random points. Okay, let's just use points that are completely out of whack. We know nothing about them, but we know uniform randomness is the most difficult one. Okay, which is actually what people do when they build encoders, right? So in order to make sure sort of Zoom works, Zoom for sure had random noise passing through the Zoom network. Now, what happens when you do that? What happens when you do that is amazing. When you do that is you can do that empirically, which we did, and I'll show you next lecture. What happens when you do that is you find out two things. You find out it follows a curve like this, which I need to explain. And the other thing is you find out actually that curve is explained by something that was already invented in 1852 by a guy called Schläfli. So Schläfli was a math teacher in Switzerland, a high school math teacher, not even college. And he, because he was in Switzerland, spoke 3 languages: French, Italian, and German. And what happened is that the Italians went in, and you know, so there was a Hilbert wanted him to translate his work to, I think, Poincaré. So some high society mathematics meeting. You should look it up. And they needed a translator that was math savvy enough to do math translations. I mean, math is mostly formulas anyway, but hey, there's some words in between, and for that, let's use somebody who's a native speaker of these different languages and knows about math. So they chose Schläfli. And now, in the days of 1850s, and actually before that, 1830s, this is not a small feat, okay? Schläfli had to travel with Hilbert and I think, again, Poincaré, and really sort of with them as they met all the time and took, you know, a year off to do that. And then he came back and his mind was completely changed because he was just exposed to the inner workings of two mathematical geniuses, and he was a pretty good anyway because they chose him, right? He goes and says, yes, I know, I'm just a small math teacher in this random high school, but I learned some things and I have some ideas that I really need to write down. And what he did was he invented literally linear algebra and algebra, because his idea was, could we use algebraic things to describe geometry? And he wrote in a monography, an essential monography, and he asked really, like for a long time, that the most important mathematical publication corpus, which was the imperial sort of mathematical society in Germany under the emperor that Germany had at the time, that they published this, and they did in 1852. He actually saw it published, but he then died after it pretty soon. A sad story as usual. Scientists never get the fruits of their thing. But what he did is, he did not only invent sort of computation, so basically geometrical algebra, he also came up with a formula that describes how many linear separations you can make out of random different points. And this is the formula. He derived it from the Pascal triangle. And it basically says, this is what is called the TNK function. The TNK function is the number of distinct threshold functions on n points in general or random position in k dimensions. What you can do here is you say, n is the number of rows in my table, and k is the number of parameters in my perceptron. And so if you do that, then what happens is that n becomes 4, right, for the Minsky problem, and k becomes 3 because the perceptron has two weights and one threshold. So we would have to calculate t for 3. And let's do that. And if you do so, where is that? If you go t for 3, where's my, I'm trying to find my, okay, do people see that? If you go in the y-axis down, for n is 4, and in the x-axis to k is 3, you see the number 14. Okay, can everybody see that? Okay, so t for 3 is 14, and the answer is yes. If you have 4 points, 4 rows to label in binary, and you have 3 parameters in a perceptron, 14 of them work, okay? And now the interesting point is that in the end, if you have 4 parameters, it's 16, and that means you can label them all. So that in the end, you need as many parameters in your perceptron, which is technically not always possible. But in the end, the solution is you need as many parameters in your perceptron than you have in your lookup table to guarantee that everything can be labeled. Any idea why that is? It's even more profound than that. I'm just gonna ask randomly. Again, don't feel personally intimidated. It's okay, okay? I just wanted to keep thinking. Sai, any idea why that is? Sai? Okay.
Oh, hey, could you ask the question again?
Yeah, I'm asking the question again. The question is, why is it that in the end you need as many parameters in your perceptron than you would need than in your lookup table to guarantee that all functions can be labeled? Just pick a random guess.
Is it just because, like, even when you solve linear equations, like if you have that many unknowns, you need that many linear equations in order to solve all those unknowns?
First of all, that is correct. When you have n linear equations, you can have n linear solutions, right? That is first of all correct too. First of all, I take this as an answer. It's not what I expected to hear, but it works, okay? There's another answer. Let's see. Randy? Oh, I had you before, right? Eleanor is still on?
Yes, sorry.
Yeah, Eleanor, any clue on a higher level? So the argument with the equations is completely correct. Now I'm trying to find an argument that's even more universal than that. Just pick a guess. If you cannot come up with something, it's fine too. But what could it be?
I mean, the needing that many variables to solve a linear equation made sense to me. I'm not immediately sure about the more general argument.
Okay, so I'm giving you the more general argument. The more general argument is universal lossless compression doesn't exist. Okay, so what we can say is this. You can reformulate something into something shorter, but not universally. Or you can lose something, okay? So here's what happens. If you were able, and this is the proof by contradiction, there's a better proof that I'm gonna send you a lecture video for, okay? You're gonna get this week a lecture video, an extra one, just for the proof of what I mean with universal lossless compression is impossible. But humor me for a second. You take a file and you zip it, okay? Now it's shorter. Now let's take that same file again and zip it again. Well, now it's shorter. And then take it again, zip it again, now it's shorter. So if you could compress everything all the time and just make it shorter, why are we compressing everything down to, like, say, 1 bit? We cannot. So the problem is this. Some files will actually grow larger when you zip them, and some files will grow slower. And on average, and in the end, to guarantee that you can handle all files, you can't actually compress. This is the same as no free lunch. There's always a cost to lunch. You know, you can shift it and make it disappear and so on for a narrow viewpoint, but the overall universal viewpoint is you can actually not compress. What it means is you can actually not do anything else but memorize. It's just sometimes you can do more in a concrete case. So if a file has a lot of repetitions, zip will make it shorter, but only once. After that, you cannot compress anymore. And if you could universally compress each file, then my question would be, why can't you compress a zip file again? And I actually want you to try this out. Zip a file, zip it again. You'll see nothing happens. It'll stay the same. Because zip knows, oops, this is not compressible for me. Because if it was, we could, by further induction, just zip and zip and zip and zip and zip again, and it would be infinitely small. So that is the reason. So what we are doing here when we're trying to put a encode a 4 labels into 3 parameters is we're doing compression. And it turns out that's the problem. You cannot universally compress. You can compress pretty well. You can compress 14 of the 16 different 4 label combinations into 3 parameters. Congratulations. It's a pretty cool compressor. But certain things like equality just cannot be compressed. In order to decide equality, you need to check every single item, full stop. In order to find out that the word Harry Potter does not, the entire book of Harry Potter does not contain the word bubbly-doodah, I don't know, just coming up with a random word. To really confirm that, you need to read the entire Harry Potter and confirm that hypothesis. There's nothing you can generalize about it. Some things cannot be generalized, some things cannot be compressed. What it means is every compression is special. And now the question here is, how special is a perceptron? And that was then answered by Cover and McKay, and they came up with this function. So what you do is, you now go and say, let's plot this function. So this function in a matrix is just what I showed you, n and k. And when n equals k, then you can encode all functions. But when k is larger than n, obviously you can also encode all functions because you have way too many parameters for the function. But when n is smaller than k, things are kind of interesting, right? Because then it's 14 and 8 and 22 and 30 and sort of this on the left of the diagonal. And he plotted the left of the diagonal this way. So he said, on the y-axis is the probability that I can encode a function, right? So that would be 1 for n, right? For in the beginning for n equals k or k greater than n. So what he on the or maximally 1, and on the x-axis, what we have here is n divided by k. That means n is the number of labelings, the number of rows, literally, in your table of binary labels, and k is the number of parameters in your perceptron. And then you just divide the two, and you figure out, obviously, when the ratio is smaller than 1, that means you have less labels than parameters. The probability that you can encode that function is 1. But the surprising part is, when you have n divided by k approaching 2 for a very large number of k and very large number of n, then actually there is some kind of universal compression going on. That is only a kind, because that is in infinity, okay? The curves will drop if you actually measure them, and I'll show you measurements of the curve, will drop much earlier, okay? But in infinity, there could be a compression, and this compression factor is 2, okay? It's the same as saying the information capacity of a perceptron is 2. The supremum of the mutual information is 2. So what this does is it says that even for uniform random points, you will have, you can expect to only use about, for almost all functions you have, you can expect to almost use about only half of the number of parameters than the number of labels. And that's very interesting. But here's a problem. Here's where I come in as an engineer and say, I love this result. How cool is that? We finally understood what a perceptron, the power of the perceptron. But it doesn't help me as an engineer. Because as an engineer, I go and say, yeah, it's nice that I have a high probability to be able to encode this stuff. But I actually want to guarantee. I want to guarantee that I can encode this stuff. And so now there are 2 points of this curve that will be the most important points. We have the point where n equals k. That gives me a guarantee. Whatever function you put in there, it can be overfit. It can be represented by the perceptron and can be memorized. And that for me is the memory equivalent capacity. The memory equivalent capacity is n equals k. You are at memory equivalent capacity in a perceptron when the number of parameters of your perceptron is the number of rows in your binary labeling table. That is it. Now, that also coincides with the VC dimensions for uniform random points. And it has to, because we can do our labelings. And now, the cover McKay information capacity is saying, yeah, but if you just want to look at the probability in infinite, for infinite number of attributes, then it's actually 2. And once you get above 2, it's very unlikely that you can do something because it's really steep. We will measure this. I will show you how we measure this to be true. And this basically is very, very interesting because it shows you that a perceptron is inherently a good idea when you want to generalize. That is the reason why we're all gung-ho about perceptrons. Now, next lecture, and after you did your homework, and after you saw some extra lectures that I will put on, I will talk to you about how to generalize this result to not just one neuron, but to a bunch of neurons, to an actual neural network. To find out, okay, I have n rows in my table. What is the probability that my neural network can do this? Okay. And if the probability is too low, you need to increase your network. And if the probability is too high, you should probably decrease your training time because you don't need so many parameters. Just use less parameters, okay? So that is the first way of approaching this. There's gonna be a lot more. But right now, you can use this after you learn how to deal with neural networks to size your network. That answers the problem of, once I gave you the rules for how to combine perceptrons, that will answer your problem of the size of your network, your expected size of your network, because this answered the problem of the expected number of parameters of a single perceptron and how powerful they are. So again, this is a single perceptron. Now for neural network, we created the theory and how to do it. And I was very challenged because the trick was in the beginning that we were actually kind of distracted by this architecture that you see here, a multi-layer deep learning architecture. It turns out though, if you look at XOR or not XOR, how do you actually solve that in real? Yes, you could do the left approach. And if you do the math, you'll actually see that this neuron actually does it. Okay, that gives you solution to XOR of X1 and X2, and it's called a multi-layer perceptron, okay, MLP, or in modern words, layered network. And on the right, you have something else. It's 2 neurons also solving XOR. It's called a shortcut network. And the interesting thing about a shortcut network is that it uses less parameters than the left one. Right? Because the left one uses 1, 2, 3, 4, 5, 6, 7, 8, 9, and the right one uses 1, 2, 3, 4, 5, 6, 7. Right? Now, that's interesting because less parameters save some problems, seems like some efficiency. Turns out, if you try to train the right one, it's a lot harder. But we know this one. Did Microsoft, Facebook, I don't know, reinvent this? This is called ResNet. A ResNet is where you have connections from layers that jump layers. Well, that's what that is. It's called a shortcut network, but of course, it was reinvented by the big people right now, and they're called a ResNet. Now, we will understand, we will next lecture go through how to get to the memory equivalent capacity and the McKay curve, basically, of these 2 networks. So then you can then compare to the lookup table, which is easy. That's just n bits with n being the number of rows, and try to size your network according to your data that you have. And that's going to be basically the result of next lecture. And you can see as how that immediately leads you to working on your project and understanding other research. And Obviously, we will go much further than that, though. I will show you a bunch of more stuff that you can do. But this is why I said these next 2 lectures are sort of the main essence. If you want to play around with it immediately, there's a bunch, these rules are on the cheat sheet. These rules were also in the generalization lecture. There's the TF meter application, the demo that I definitely want you to take a look at, but we can do this all next time. There's no rush. For now, just get a little more familiar with information, and the way I suggest to do that is to take a look at the homework that is already online. And then also, it never hurts to actually take a quick look at McKay of how he went through to solve Minsky's problem. Other than that, please stay safe, stay indoors, the air is really bad. And thank you very much. The lecture will be online, and hopefully that helps you. I will stop the lecture so you can ask questions. I will stop the recording so you can ask questions. Stop recording.